Good morning or afternoon, everyone. Thanks for letting us join your science meeting and share a little bit about what we do in deep space exploration within Lockheed Martin. As Alex mentioned, I'm Ryan Pfeiffer, the program manager for Curio, which is our deep space capable smallsat architecture. We've been developing Curio since 2019, based upon our deep space heritage, which Joe's going to talk about a little bit more here, going back over 50 years. Curio allows us to apply this decades-long expertise to smaller, faster, lower-cost missions that don't necessarily fit the mold of more traditional opportunities. The BEX mission is really exciting for us. I was looking at the chart that Dan showed. We've been involved with many of those missions over the years that he shared. So this is another really exciting one for us. Lets us partner with SAO, a world-class institution, and execute an incredibly exciting scientific endeavor to further study the property of black holes, and hopefully make a whole new set of friends and partners while we're at it. Enabling scientific progress is our passion, as I hope comes across in this presentation that we're going to share with you here. So yeah, over the next 20 minutes or so, we'll go through our overview of our history and capabilities, and then leave some time for questions at the end. And with that, I'd like to introduce the Curio architect, Dr. Joseph Schoer. Make sure to ask him the hard questions, and I'll take the easy ones. And if we have the really hard questions, I think we have Whitley Poyser, our deep space exploration director, online as well. So with that, Joe, go ahead.
Yeah, thanks, Ryan. Just to check, can you hear me okay?
Yes, we can hear you great.
Okay, excellent. Yeah, we actually thought that rather than go through the details of the BEX spacecraft specifically, we would kind of take a step back, since not all the team might be familiar with the Lockheed Martin space business area and our role on science missions, and what we can actually do at our facility. So we wanted to kind of provide that overview, and if you want more details on BEX specifically, we can come back at a later meeting. So Ryan and I and Whitley are from Lockheed Martin's space business area in the deep space exploration mission area. Lockheed Martin Space is based in Denver in Colorado, and we also have some sites in Sunnyvale, California, and Huntsville, Alabama. Those are our kind of major locations. And we've actually been building spacecraft for deep space missions for 50 years now, starting from the Viking 1 Mars lander. So I have a neat video that our communications team put together celebrating that event. I think I've set my screen share up so that sound will come through, but it's subtitled if that's not coming through okay. Or maybe Ryan, you can post the link in the chat. So I'll give this a play here. Let's see.
50 years ago, Viking 1 took to the skies and ushered in a new wave of scientific discoveries. Built and launched by Lockheed Martin, Viking 1 was the first NASA spacecraft to land on Mars and send back images from the surface. This mission marked the beginning of our company's deep space legacy, one that would reach every planet in the solar system and redefine what's possible. The spacecraft we've built over the decades have unveiled the mysteries of Venus beneath its clouds, captured stunning imagery of the universe, and have unlocked the secrets of Jupiter and its moons. We have journeyed to multiple asteroids and comets, and have even brought back samples, giving us key insights into the formation of our solar system. And we've proudly been a part of every NASA mission to Mars, building the spacecraft for half of those 22 missions. We've helped decode the Martian atmosphere, mapped its surface, and investigated the presence of water, which could be an indicator of past life. Our aeroshell and heat shield technology has enabled the entry, descent, and landing of every NASA mission to the surface. And for more than 215,000 orbits, we have been operating NASA's 3 current Martian orbiters, which provide critical communications infrastructure. For the past 50 years, these deep space missions have informed every step forward, fueling discoveries, guiding future human exploration, and inspiring the next generation to ask, where do we come from? Where are we going? Are we alone? Science is at the heart of why we explore. What will the next 50 years of deep space missions enable?
All right, I love that our public affairs team put that together, because we really do care deeply about the science for the missions that we build spacecraft for, and it really they highlighted that. So that's the main, as Ryan said, that's the main sentiment that we want to convey today. So when I say deep space exploration, that's kind of a loose umbrella term for us, meaning the robotic science spacecraft that we build primarily for NASA's planetary science division in the Science Mission Directorate, but also some heliophysics and astrophysics spacecraft as well. This chart places our deep space science missions on a timeline. As the video pointed out, these spacecraft have visited Jupiter, Venus, asteroids, comets, the moon, all over the solar system. And we're particularly proud of our involvement with Mars exploration with NASA. So this chart actually contains 3 Mars orbiters and 4 landers. That's just a large number of spacecraft going to the red planet. All of those built in our Denver, Colorado facility. So in development, we have Venus missions, Veritas and Da Vinci, the Aeroshell for the Dragonfly, lander on Titan, and then a potential mission to the asteroid Apophis, as well as some elements of Mars sample return. So we're very active still, at multiple destinations across the solar system. And just to highlight that even further, this is another view of kind of the role that Lockheed Martin has had specifically in planetary exploration, organized by location in the solar system. We've been involved with the exploration of every planet and many minor planets and comets and other bodies, and not just building the spacecraft, but also components, heat shields, instruments, cryocoolers, propulsion systems, solar arrays, different pieces of the spacecraft system, mission operations. I'll talk more about that a little later. So on this chart, the mission names with an asterisk are ones where we built the whole spacecraft, but other ones we've contributed portions as well. So we've got expertise across many subject matter domains. When I say spacecraft, the instrument is really the source of the science mission, and so that's what we all want to highlight and accomplish the instrument's mission. The spacecraft is the platform that it stands on. It provides power, it provides a thermal environment, communication to the ground, an orientation in space, controlling that orientation, propulsion if necessary to get to some orbit or some destination, as well as the mechanical structure to hold it all. And we build and design many of those subsystems for a spacecraft at our Waterton Canyon facility in Colorado. We build our own structures, avionics boxes, propulsion systems, thermal blankets, harnessing. We have machine shops, we have electronics shops, we have a propulsion lab on campus, many test chambers. Some of the subsystems, like attitude control, for example, we will design the system, choose components, and then integrate it together from components that come from other suppliers. So we have both things that we can build ourselves, and then we're comfortable integrating components that come from other vendors. This image is actually of the OSIRIS-REx spacecraft in the early stages of integration. So OSIRIS-REx here has its structure and propulsion installed. The main propellant tank is in that center column, and then those red covers are covering up the thrusters. Next will come electronics boxes, and then finally a thermal blanketing around the spacecraft, as well as the instruments. One of the items that we build ourselves is solar arrays. We have a large solar array production facility in Sunnyvale, California. we build solar arrays that run the gamut in terms of size, all the way from the International Space Station arrays, which are bigger than the one in this photo, down to small sat solar arrays that might be, you know, a human arm span or smaller. So this solar array that you're looking at here is one of our newer flex solar array configurations. When deployed, it produces about 12 kilowatts for some of our geostationary communications missions, but then it packs down to that stowed envelope that you see in the foreground. So it's very efficient packing there. Our facility has the electronics design, they have robotic assembly systems to, you know, lay down panels for these arrays and then integrate them all together and do deployment tests like you see here. For some missions, we also have more specialized capabilities that we can bring to bear, including, you know, mechanism designs or heat shields is something that we actually do a lot of. This is the heat shield for the Mars Science Lab, the Curiosity rover. It's the second biggest kind of heat shield that we've made. The largest ones are for the Orion capsule. We've built, thinking back to that video at the beginning, the heat shields and the back shells for every NASA Mars lander. We've also built 3 aeroshells for bringing samples back from other from deep space locations to Earth. Again, all of those are at our Denver facility. We can do the thermal protection. This image that you're looking at is the, you know, velocity facing part of the heat shield, and we also do the other side, the back shell. So as we build up a spacecraft and all its subsystems, we do a lot of testing interspersed through that process. Once we have the whole spacecraft, we'll do end-to-end testing of mission operations and spacecraft operations. We design and write a lot of our own flight software, including instrument interface software, as well as any mission-specific flight software. Lucy is a great example. So this is the Lucy spacecraft that's now exploring the main belt asteroids on its way to the Jupiter Trojan asteroids. For Lucy, we developed an algorithm that takes images of the asteroid and closes a loop with spacecraft pointing to keep the target in the field of view as the spacecraft whizzes by at several kilometers per second. And so that algorithm, that targeting algorithm, is something that got a lot of testing attention during our design and test process. Our preferred method to do kind of integrated level testing is to test as we fly. So we'll run those kind of test scenarios from our mission operations center. We'll have simulators active on the spacecraft so that it thinks it's in space and go through realistic operations. For something like BEX, we might, you know, we haven't gone through all the detailed planning for this, but, you know, we might think about you know, having an RF source that the antenna receives and you know, having a laser receiver that the laser comm can talk to, just to show that you know, that pipeline is intact and producing the data that we expect. So that might be the kind of example of things we might consider as we get further into this. Another role we've had in astrophysics missions is instrument development. So our Advanced Technology Center in Palo Alto built NIRCam, the primary camera instrument for JWST. ATC has also built spacecraft and instruments for some heliophysics missions, IRIS and MUSE. And they're working on many other technologies that go into instrument development, including some of the world's smallest cryocoolers, as well as some interesting active vibration isolation systems. It's really our technology research and development lab. We also integrate instruments from other providers, universities, foreign sources as well. This is the InSight Mars lander. The primary instrument there came from France, and then it had a penetrator that drilled down into the Martian surface a bit. That came from Germany. So lots of different suppliers and types of instruments there. Here, the spacecraft is going through landed testing, pretending it's on the surface of Mars. So we're checking out that we can communicate with all the instruments and get the data we expect. I briefly mentioned test chambers earlier. This is OSIRIS-REx with the once the spacecraft is fully assembled, getting lowered into our largest thermal vacuum chamber at the Waterton campus. So we'll do a full suite of environmental testing. We have test chambers and facilities for thermal vacuum, electromagnetic interference and compatibility, vibration testing, all kinds of different instrument, subsystem, and spacecraft level tests. And a kind of an unsung hero through this whole process is the project management that we do. Our planetary missions often have to hit like a specific launch window, and OSIRIS-REx has one of the best anecdotes illustrating our project management, in my opinion, anyway. So this mission launched from Earth, went to an asteroid, mapped it, came in, grabbed a sample, came back to Earth, and dropped the sample back at Earth. The date of the landing of that sample was actually within 24 hours of the original proposed date in the Step 1 proposal. So from 2009, when that Step 1 proposal went in, to 2023, when it landed, in some sense, this is a tautological statement. Like the mission design is what it is. The trajectory just is what it is. But when you back off from that landing date, that not only did we have to execute that trajectory, but testing, building, design, the Step 1 proposal, the Phase A concept study, all that, had to get nailed on a timeline to achieve that kind of performance. Of course, I couldn't be talking to an astrophysics group without mentioning that Lockheed Martin built the Hubble Space Telescope in Sunnyvale. Here it is in the high bay, looking enormous. We also built the Spitzer Space Telescope and operated it until just a few years ago. And we've worked on astrophysics concept studies from SMECS to probe class. So we do have we have a lot of planetary missions that we like to talk about, but we also have an astrophysics presence as well. And of course, we've made many Earth orbiters, civil, commercial, military, communication satellites, Earth observation spacecraft, weather spacecraft. The two spacecraft in this photo are GPS-3 vehicles. So we've now launched 8 of these for the U.S. Air Force and Space Force. I like to point them out because everyone uses GPS every day. We've also built the latest GOES series of weather observation satellites for NOAA and communication satellites. One of the companies out there that's bought several communication satellites from us is SkyPerfect JSat in Japan. So we have a number of international relationships through that line of business. One of the things that this long record of Earth orbiting spacecraft experience gives us is, we have engineers with a deep understanding of all the components on them. And that translates directly to our science missions because we'll use a lot of the same technologies and components on our science missions. So even a mission like a SMECS mission where Janice mentioned we're budget constrained, but we can go pull an expert in many different disciplines or particular components if we need them. In addition to building the spacecraft for science missions, we do have a dedicated mission operations center for our deep space spacecraft. It connects with the Deep Space Network, with NASA centers, with science operations centers in multiple locations. It's conducted ops for 17 spacecraft, including 7 that are still flying now. So on this slide, InSight has completed its mission, but the others are all still active. And you see in the photo there, they are celebrating the sample acquisition of OSIRIS-REx, which was a real highlight for that team. A relatively new effort for Lockheed Martin Space over the last few years has been our push to building small satellites for science missions. We call them our Curio spacecraft. Ryan introduced that, mentioned that term in his introduction. Our first launch was Lunar Trailblazer, and we're hoping to reuse the 2 almost completed Janus spacecraft on a mission to the asteroid Apophis. On that mission, actually, we're working with a consortium called the Milo Institute to fund the mission independently of NASA's traditional PI-led competed missions. So there's an interesting array of business models that our small spacecraft kind of are getting us into. And this overall has been a learning experience for us. One of our key lessons has been that even on these small, lower cost missions, we still need to emphasize engineering fundamentals as we've demonstrated them on the larger spacecraft as well. Whatever the size of spacecraft we're working on, one of our key principles is to work closely with the science team every step of the way. So here you see Dan Shears on the left is the PI for the Janus mission, and he's with our mechanical systems lead as they inspect his spacecraft during their assembly and test. We worked with Dan all the way back in the Janus proposal to formulate the mission, connect the technical implementation to the science objectives, developing the science traceability matrix, mission traceability matrix, all the proposal material. That included handling proposal management, document preparation, graphics, stuff like that, to really create that through line in the proposal that every subsystem, every aspect of the mission was supporting the science. And then that continued during development as well. We maintain working groups with the science team to hash out the fine details of critical science operations. That's pretty typical for us. We actually have some scientists on our staff. One was on the Janus science team to help further facilitate that integration between the engineering side and the science investigation. And that's what we want to bring to Bex. So we're really just, everyone is ecstatic to be you're working on such a cool mission, and working with another great institution in the Center for Astrophysics to open a new window on the cosmos. So we've been working to build that relationship with Michael, with the rest of the science team, with Dan and the instrument team. And we want to continue developing that. We love solving the problems this mission is challenging us with because of the cool discoveries that we think are going to come out of this. So we want to keep talking about how we can start out as strongly as possible when that AO drops. So yeah, with that, I'll turn it back over to the floor with the statement that we're all excited, and go Bex.
Go Bex. Thank you. Yeah, by the way, I should say I love the video trailer at the start, and I'm very excited to see the updated version with Bex at the end. I think it'll make it even better.
Definitely.
It will.
Definitely.
Can't wait.
So thank you so much to the 3 of you for being here. I think we have time for some questions. And while people think of one, I actually have a question. What is the scale for the Curio missions? Sort of the rough estimate of the cost? I don't know if that's public or not, but just they're smaller than SMEX's, I take it, right?
Yeah, and Ryan, feel free to chime in here. The Curio spacecraft as a common platform is made to support that lower cost mission class. So whether it's like in the SMEX region, we've also seen it be applicable to other low cost missions that whether it's like in the commercial lunar payload kind of community, but that is the mission class we are targeting. And then of course, because we prioritize supporting science, we want to make sure that we also can work that architecture with the science instruments But yeah, Ryan, I don't know if there's anything else you want to add.
Yeah, it's a little hard to put an exact dollar figure on Curio because it's designed to be adaptable, right, for the different mission that we're approaching, and that adaptability, of course, takes different forms. And so, you know, definitely well within the SMEX category is what it's targeted at. Previously, Simplex, as Joe mentioned, Janus and LTB were in the Simplex class. So definitely that range of cost cap missions is what we're targeting.